Hello, everyone, and welcome to Backer Breaks It Down. In this episode, we continue to look at power functions and their graphs. Now, the graph here features many types of power functions. Okay, you will notice that there's a lot going on in quadrant one. So our power functions, they definitely have something going on in quadrant one if and only if k is positive. So all these functions that you're seeing here, they're of the form k times x to the a power. And in all of these, k is positive. So we notice that when k is positive, all of our functions definitely have something going on in quadrant one. All right. So if k were negative, then there'd be stuff going on in quadrant four. Another thing you notice is that they're all intersecting right there, okay? So that point where they're all intersecting is the point 1 comma k. So it's very much dependent on the value of k, what that point is. Sorry, I don't know why my pen's not working that great. Notice that some of our graphs pass through the origin and some of them don't, okay? So all power functions contain the point 1 comma k. That was that common point they were all passing through, okay? If a is greater than 0, then the graph passes through 0, 0. And if a is less than 0, then it's asymptotic to both axes. So if you're wondering like what asymptotic is, let me highlight for you here. So notice that this graph in orange doesn't pass through 0, 0, and it's getting really, really close to the x-axis, but not crossing or touching it, and it's getting really, really close to the y-axis, but it's not crossing or touching it. So that's what we mean when we say they're asymptotic to both axes, okay? But basically, it'll do one of two things. It'll pass through 0, 0, or it'll be asymptotic, and it's all very much dependent on the value of a. A is your exponent. So if your exponent is positive, your graph will pass through 0, 0. And if your exponent is negative, then it's going to be asymptotic to both axes. So if I were to go back to some graphs we looked at in the first episode, okay, so here we have even positive numbers. So a is greater than 0. And look, it's passing through 0, 0. Here we have odd positive. So a is greater than 0. The graph is passing through 0, 0. Here we have even negative. Notice this graph does not pass through 0, 0. We are seeing that asymptotic behavior. Likewise, with odd negative, we're seeing that asymptotic behavior, okay? So power functions have 4 possible shapes, and we're talking about what's happening in quadrant 1, of course, unless it's been flipped. So we will be in quadrant 1 whenever k is greater than 0, right? And there are 4 possible shapes in quadrant 1. The green curve is when a, the exponent, is negative. The red curve is when the exponent is greater than 1. The black line is when the exponent equals 1. And the blue curve is when the exponent is in between 0 and 1. Now notice you have basically reflections of these in quadrant 4, which makes sense because quadrant 4 is when k is negative. So the green graph is when a is less than 0. The red curve is when a is greater than 1. The black line is when a equals 1. And the blue curve is when a is in between 0 and 1. So the parameters k and a tell us quite a bit about a power function's graph and what it looks like. Remember, we can also use the parameters of k and a to tell us about end behavior. All right, so we're going to analyze graphs of power functions, and this section in your notes, like this screenshot that I'm giving you right here, this is in your notes. on page 5, you definitely want to be looking at it, like have your notes open to this page when you're doing such problems. All right. Okay. I put a little screenshot at the top to make it a little bit easier for us. So in number 7, we're analyzing the function f of x equals negative 2x to the 6th power. That is perfect power function form. So I can easily identify k. K is negative 2. And I can easily identify A. A is 6. Now, when it comes to the graph, I need to pay attention to what quadrant am I in? Well, since K is negative 2, that means it's less than 0, so that means I'm in quadrant 4. The value of A is 6, and 6 is a number that is greater than 1. So we are looking at graph G. Contains the point. Well, it says right here, the graph contains the point 1 comma K. So that means our graph contains the point 1 comma negative 2. Does it pass through 0, 0, or is it asymptotic to both axes? Well, it all comes down to the value of A. Is A greater than 0, or is A less than 0? In this problem, A is 6, so that means it's greater than 0, which means the graph passes through 0, 0. And then we have our end behavior. Okay, so I'm just going to scroll up because I have my end behavior summary right here at the bottom. And it all comes down to first, like, what's the exponent? The exponent is an even integer. Okay, now be careful because that negative 2 means it's been flipped. So it's not going to be positive infinity on the left and the right because it's been flipped. What that means is it's going to be negative infinity on the left and negative infinity on the right. But it's pretty simple so long as you are looking at that graphic on page 5 in your notes, right? So let's try another one. In number 8, we have the function f of x equals 3 over 4x to the 5th. Now, this is not true power function form, which is why it says to rewrite it in the form k times x to the a power. Well, the 3/4 is fine, because that's just going to be the value of k. The x to the 5th needs to come out of the denominator. We cannot leave it on the bottom. So we're going to bring it up. And so remember, when we move it, the attitude of the exponent changes. So now our exponent is going to be negative 5. So k is 3 over 4. A is negative 5. K is greater than 0, so we are in quadrant 1. Since A is negative 5, we're looking at graph A. Contains the point. All power functions contain the point 1 comma K, which means that this one contains the point 1 comma 3 over 4. Does it pass through 0, 0, or is it asymptotic to both axes? Well, this all comes down to the value of A. Our A value is negative 5, so if A is less than 0, that means it is asymptotic to both axes. For the end behavior, got my summary here. Okay, it all comes down first to that exponent. Our exponent is negative 5, so it's a negative odd integer, which means no matter what, the end behavior is 0. So pause, try 9 and 10, check back in with me. We'll see how you did. All right, so in number 9, I first need to rewrite this power function. All right, and so I'm going to have 3x to the 1/4 power. The value of k is 3. The value of a is 1/4. Since k is positive, I'm in quadrant 1. And since it's 3, we're looking at curve B. All of these graphs contain the point 1 comma k, so we're looking at 1 comma 3. And when it comes to what else does it do, since a is 1/4, that's greater than 0, it's going to pass through 0, 0. For the end behavior, now comes down to my exponent, and my exponent is 1/4, which is 1 over an even integer. And since k is positive, that is my end behavior. So the left end behavior does not exist. And then the right end behavior is infinity. And then in number 10, first I need to rewrite this. So I would have -1/2 x to the 1/3 power. K is -1/2. A is 1/3. Since k is negative, we are in quadrant 4. Since A is 1/3, we're looking at graph E. 1/3 is in between 0 and 1. This function contains the point 1 comma -1/2. And since A is positive, it's going to pass through 0, 0. Now my end behavior, I'm working with a rational exponent with an odd denominator, okay? I have to be careful because k is negative, which means it's been flipped. So that means my end behavior gets flipped as well. So that means on the left, it would be positive infinity, and on the right, it would be negative infinity. Sorry, I don't know why this isn't writing. Okay. And that's how you analyze a power function. So we're focusing on the values of k and a. They tell us quite a bit about our function. The value of k will tell us a point the graph contains. It'll tell us definitely which quadrant, 1 or 2, the graph appears in. The exponent will tell us specifically what shape our power function has, whether or not it passes through 0, 0, or is asymptotic to both axes, and both of these can be used to determine end behavior. And that is how Bakker breaks it down.